That's what we want to know, right? So we're happy to see that. Constant, constant, constant. Shit, A. I don't know what A is, do I? At the moment in time, do I? I don't. All I know is I know the volume at the moment in time, right? I don't know the area. So I don't know that, so I'm not happy about that. dA dt, I actually know, don't I? So in order for me to answer this question, to figure out what dV dt is, I'm going to need to know what A is. So time for us to go find A. We need A. Well, here's what I know. I know that the volume is 36. I'm just going to leave it 36 pi, right? Don't I know that? Now I'm talking about the instant in time. The volume is 36 pi. But volume, the definition for volume was what? 4/3 pi r cubed? So 4/3 pi r cubed equals 36 pi, right? The volume of a sphere is 4/3 pi r cubed, and that must be equal to 36 pi. Let's solve this for r. And I think I made this problem work out pretty nice. You can divide both sides by pi, right? And then you can multiply both sides by the reciprocal, 3/4, 3/4. You get r cubed equals, what is that? Is it 27? Yeah, 27. Right? 36 divided by 4 is 9. 9 times 3 is 27. What number cubed is 27? 3. So r is 3. 3 what? Feet, right? Feet. The radius is 3 feet. Now that's not what we're looking for. We're looking for the area, right? But we have the area formula. What's the area formula? Area is 4 pi r squared, right? And so I know that the area for us would be 4 pi times 3 squared, because the radius is 3. So the area must be 36 pi? Ooh, don't get it confused. This is square feet. It's just a coincidence that the area looks like the volume, all right? It's just a coincidence. This is square feet. It's an area. This is cubic feet. Totally different measurements, right? But now I have this, don't I? I have this. So I'm ready to get a final answer here. It's fun, right? So dV dt equals 1/3 square root of 4 pi times 3/2. Okay, a to the half is the same as square root, right? So square root of what? Square root of 36 pi. And then what's still there? That's square root of 36 pi. dA dt? 20. There. We just need to figure out what this is. Can I convince you to look at this and this together? Since there's a root, this one is like on top, right? This one's in the denominator. Couldn't you put those together into one fraction, 36 pi over 4 pi like that? Couldn't you do that? That's a property of roots. If you had a root on top of a root, you could put them together, couldn't you? And then you just put whatever's in here over whatever's in there. So that's correct, right? And this is just 9. Square root of 9 is 3. So everything in green here is going to just turn out to be a 3. I'll just tack it to the end. Understand? Now I think things clean up. Let's see. What's the only thing left there? 10 times 3? 30? 30. dV dt is 30. 30 what? Feet cubed per second. Feet cubed per second. There you go. Welcome to related rates. Yeah, the ladder's just like the first classic problem, right? That just kind of gets you to get the idea here. This is hard, okay? I will admit this is a hard problem because of this whole having to make the connection between V and A. That's hard. I probably wouldn't give you a problem like that on a test unless it would be something like a bonus. Let's do another one. We're spending 2 days on this. Go ahead and read that problem. Normally what I do on the next exam for this topic, what I normally do is give you like 4 or 5 of these problems and have you choose 2. Right? So like you get to the test, I give you a selection of these problems, you get to read through them, you get to pick 2 of them out of the 4 or so. That way, if one of them you feel a little more comfortable with the, what's going on, geometry, things like that, then, you know what I mean? Does that make sense? So it gives you some sort of like relief valve just in case, right? If I give you one problem and it happens to be one problem you don't understand, then that's not good, right? All right, this plane is flying horizontally at an altitude of 2 miles. We are going to neglect the curvature of the Earth here. We're going to assume that the Earth is flat, although it is flat, right? So we're going to assume the Earth is flat for the sake of this problem. And we have a plane flying overhead horizontally at an altitude of 2 miles, and it's traveling at 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment the plane is 6 miles from the radar station, how fast is the distance between them changing? I'm going to draw the general picture first. All right? Here's the ground. Here's my radar station on the ground.
You're the radar.
Thank you. It's years of practice, so don't feel bad if you can't match the quality of that radar. Just put a point, okay, and label it R or something if you want. Okay, that's our radar on the ground, right? And then you have a plane flying overhead. Ooh, ready to see my plane? Oh, I already messed up. That's too big. I don't want that plane that big. So maybe something like what? What's the problem? Obviously, oh, it's missing the other wing. There we go. All right, so there's my plane flying overhead, right? I'm starting to read the information here. It's traveling, this thing is traveling at a certain speed, right? 600 miles per hour. That is not a length of anything, right? It's just the speed at which that plane's moving. So I'm just just to remind myself, this thing's moving this way at 600 miles per hour. Look, you could have drawn your plane on this side and have it come this way. It doesn't matter, okay? I just chose to bring my plane from the left to the right. What else? 2 miles off the ground. That's not changing, is it? That's the same no matter what, no matter if I'm in the instant or in this picture. So the distance from here to here is 2 miles, fixed. 2 mi. All right? Bless you, bless you. All right, what am I given? What do I want? All right. Question? Yeah? What? So it says, at the moment, the plane is 6 miles from the radar station, right? That's our moment in time. That would need to be in this picture. You want to draw that? Let's do it. Okay, so we have the radar station, right? We've got our plane here. My plane, it's going to be a different plane now. All right, there we go. Now, when we say distance, at the moment the plane is 6 miles from the radar station, we're talking about a direct straight line distance, not like a projection down to the ground and then 6 miles this way. We're talking about straight line distance. So we're talking about this being 6, right? That's the instant in time. And can't we still say that this is 2? Did y'all see a triangle? Okay, that might be helpful in a minute. Might not. I'm just pointing out that I do see a triangle here. See, that's the instant in time though, right? All right. What else? Anything you want to add to this? 600 miles per hour is a derivative, right? It's a speed. It's the speed of what? I mean, I know it's 600, right? I know it's 600. I know it's something dt, right? But d what dt? We need to assign a variable, dx dt. But where's x in the picture? Is it over here? No, don't. This is the instant, right? Have to look here. Where is x here? So if we're going to call this dx dt, it's on the ground?
Well, essentially, I mean, you're going horizontally. So.
Okay, so but that's an important distinction everyone needs to understand. If we were to imagine drawing a right triangle here, like this, if we label this x from here to here, does everyone agree that x is changing at 600 miles per hour? It's shrinking, isn't it? So as this plane moves this way, this point down here moves this way as well at 600 miles an hour. So this is shrinking at 600 miles an hour. That's extremely important because when I do this, I need to put here negative 600 miles per hour. Because in my picture, x is this distance from here to here, and as the plane moves from left to right, that x gets smaller. So the rate at which x changes is negative. If the plane was over there going the other direction, then x would be growing, then it would be positive. Got it? Okay, so do you see how we kind of all like did that together at the same time? Like, what is it? Okay, we'll call it x, but where's x over here? And now it all matches up, right? Okay, what now? What do we want? At the moment the plane is 6 miles from the radar station, how fast, derivative, is the distance between them changing? So we want to know d something dt, right? At the moment that, well, at what? It seems like we're missing something here. We're missing a variable, right? It is 6 miles. Yes, at something is 6, right? But what? In this picture, what's 6? The hypotenuse. So you better call it something, right? We need to call this something. H. I heard C also. We could do H, right? We call that H. Then we want to know at exactly the moment H is 6, how fast what's changing. What's the distance between them? It's H. We want to know how fast H is changing. This is the distance between them. At exactly the moment that this distance is 6, I want to know how fast this is changing. There it is. It's all set up. Okay. Equation, connecting these together. You have to look at this picture, and only this picture. What is it? X squared plus 2 squared equals h squared. 2 squared, now 2 is a constant, right? 2 is the height of the plane, so that's always going to be 2. There you go. There's your equation. X squared plus 4 equals h squared. There it is. All right, I'm going to leave the rest to you on this one because I want to show you another one before we finish up today. So you know what you would do from here? Differentiate with respect to t. And then you'll have a dx dt in there. You'll have a dh dt in there. You know what h is. You might need to figure out x. And you could get x from here because this is x, and you could solve that for x. Yes?
When you're trying to find the implicit derivative,
Yes.
you intuitively know in respect to what?
With most of these related rate problems, what you're given is a speed. So it's always like miles per hour or mile or something, inches per second, whatever it is. So that's a measurement of time on the bottom. So we'll differentiate with respect to time. I'm trying to think there's any problems in here we don't differentiate with respect to time. I think there might be one, but we have another day to talk about this, so we might get to that later. All right, I'm going to show you a different problem. It's almost the same problem, just slightly different question. Okay, you ready? Same plane, same altitude, same speed, same radar station, same moment in time. But look at what I'm asking for. At the moment the plane is 6 miles from the radar station, not how fast is the distance between them changing, but what? How fast is the angle of the radar station tracking the plane changing? So now, let's see. If I were to start this kind of over, this would still be the same, right? This would be the same. That would be the same, yes? This negative 600, I could still call this x, couldn't I? That would still be the same? But I'm not talking about h anymore, right? What am I talking about? Theta, right? I want to know how fast the angle of the radar station tracking the plane is changing. So theta, but where's theta? Right here, right? I'm going to call this theta. That's the angle of the radar station tracking the plane, right? And so as the plane goes over, that angle is changing. I like to think of this problem another way, and it's a little easier to think about it this way. Think about if you're standing like on a sidewalk next to a road and you're watching a car come down the road. And think about what your head would have to do to watch that car. Imagine the car's going pretty fast. When the car is really far away and it's coming towards you, your head is not moving very fast, right? But as the car comes closer, right, it's like you have to really move your head fast here, right? And then once it gets past you, you don't have to turn as fast to keep up with the car. Does that make sense to you? Same sort of thing here. When the plane is really far away, the angle is changing very slowly. But as the plane gets closer, it speeds up and then it slows down again. Yeah? So at a specific instant in time, I want to know how fast this angle is changing. So I want to know d theta dt. And I still want it at the moment that they're 6 miles apart, right? So I do still need to put an h here and say 6, and I do need to label this as h. I know I'm moving fast here, okay? But that's why I'm recording this, all right? Because you can go back and watch this. This is on my picture still, right? This is the new picture. I still have h here, but the thing I'm interested in is theta, how fast theta is changing. dx dt is still negative 600. What's the equation? Drum roll. You need to connect what together? Theta and x. Any equation you can think of that connects theta and x together. Cosine would work. Cosine of theta would be x over h, right? Let me write that down. Don't write this down. Let me write it down. You could use this equation. cosine theta equals x over h. Why aren't you going to use it though? If you differentiate that, tell me the things that would come out of it. Would you have a dx dt? Is there an x over there? There is. So you would get a dx dt, wouldn't you? Somewhere? Do you have dx dt here? Yes? Would you get a dh dt? Yes. Do you have dh dt over here? No. Right? Would you get a d theta dt? Yes. That's what you want, right? The problem with that trig function is it has the h. And we don't have any information about h. So although that is a relationship, I don't like the h here. So let's use tangent. Because if we use tangent, we've got a constant over the x. See that? Yes.
Do we not have h? Isn't it 6?
But we don't have dh dt. Right? We know what h is at the moment, but remember, what I was trying to get y'all to see last class is that whenever you differentiate something implicitly, we have to, at some point you have to differentiate each variable. Like you'll have to differentiate theta, x, and h. And since we're differentiating with respect to time, we're going to get a d theta dt out of this, a dh dt, and a dx dt. So that means we better have information about all of those, or we better have information about one and want the information about the other. But here we would have three things of which we only know two, or only two of them are useful. Yes?
Theoretically, if like this was, because the question before was nearly identical, if this was like the same question and it was like labeled 1 and 2, and we did find the
Yeah. If it's the same problem and you just solve for dh dt in the previous problem, you could use that and then use that equation. Absolutely, but it would have to be the same instant in time.
Yeah.
Yeah, absolutely. So, but even if, just honestly speaking to you, even if I would have done this problem as part 1 and found dh dt, I would still use tangent. Because what if I messed up dh dt? Like what if I got the first part wrong? Something's off. Then my second part's going to be wrong as well. Here, I'm eliminating the need for h completely. Okay. Good? Let's differentiate this one. I'll let you finish it, but I want to differentiate it. Yes?
How do you get that tangent theta out of this?
Right here. Tangent is opposite over adjacent. Right? Tangent of theta is opposite over adjacent. So there's my relationship. That has theta in it, it has x in it, and I'm off to differentiate it. Now here's what I'm going to do to differentiate this. There's different ways you can differentiate this. Here's how I'm going to do it. I'm going to multiply both sides by x first. That is an optional step, but I like it, okay? All I did was multiply both sides by x. Now I'm going to do the implicit. On the left side, when I do the implicit with respect to time, what am I going to have to do? What is this? Product, right there. You have a product. So let's do the product rule on that. What's the derivative of the first one? Careful. What are we differentiating with respect to?
T.
T. So what's derivative of x with respect to t? dx dt times tangent theta plus, okay. Now the derivative of tangent of something. What's derivative of tangent? Secant squared. Ooh, this is the part most students miss. You did the derivative of tangent. Now you'd have to take derivative of theta. D theta dt. Am I done? Times x. Finish up the product rule. Very good. That is the product rule on the left side of the equation. Equals 0. Okay. I don't think we're going to have enough time to start another problem, so let's finish this one. There's a lot of stuff over here. It's a mess. Let's look at what we have. dx dt. I have that, right? Happy to see that. Do I know what tangent of theta is? Actually, I do. Because I can come to this picture now, can't I?
Yeah.
If this is theta, we actually know all the sides of this triangle. From the previous problem, we know that this was, did we ever solve for this last time? We never solved for that. Okay, well, we can solve for it now. It's square root 32, right? Do I have to show that work or no? This squared plus this squared is this squared. Solve for this. Root 32. It's that squared, 36. Take away that squared, 4. Take the square root. Is that okay? Did I put that? Okay, so what's tangent of theta? That over that, right? Opposite over adjacent. So I'm going to be able to figure out what that is. Can you tell me what secant of theta is and then square that answer? Well, secant's the reciprocal of cosine, right? So you'll be able to tell me what that is. How about d theta dt? That's what I'm solving for, right? Do you know what x is at the moment in time? Yeah, well, that's x, right? So that's root 32. So you got everything. All right, let's go ahead and do it, though. dx dt is negative 600 times tangent theta. Tangent theta was the 2 over root 32 plus, okay, secant. So cosine is this over this, right? Cosine is adjacent over hypotenuse. That's cosine. Secant is the opposite of that, or reciprocal. So it's this over this, right? So it's 6 over root 32. That's secant theta squared, right? Times d theta dt, which is what I'm trying to solve for, times that, which is root 32, equals 0. There we go. It's ugly, but, you know, it is what it is. So, I'm trying to think of how I want to do this. I'll just get a calculator. How about that? I mean, I could try and get an exact answer, but the calculator I think will be better here. So what I'm going to do first, I'm going to figure out what this is, okay? So on my calculator, negative 600 times 2, divide that by the square root of 32. Oops. This, I get negative 212.13 plus, okay, over here, I'll just do it all, okay? So 6 over square root of 32. Okay, I'm trusting that times that. Okay, this I'm getting, someone hopefully can confirm, 6.36 d theta dt. So that was this together with that equals 0. Move this to this side and then divide by 6.36. So 212.13 divided by 6.36. I get d theta dt is 33 I'll just say 0.4. Anyone else get that or no? Yes? Okay, I'll feel better if someone else does. This is our answer. What though? So what is our unit of time that we measured in this problem? Hour, right? Hour. So this is going to be something per hour, right? But what? Theta. What's the measurement of the angle? Well, there's no, they don't tell us anything, right? Your answers are always in radians. Always. Unless it specifically says degrees, all right? It's always radians. So this is radians per hour. You just put rad on top for radians. A plane is flying 2 miles high at 600 miles per hour over a track, coming up on a radar tracking station. The radar tracking station has anti-aircraft guns on it, right? And is tracking this to shoot it down. And it needs to know how fast to be rotating, right, at an instant to be able to keep up with it, yes? So the computer needs to be able to calculate that rotation at every instant in time. It needs to know. So it needs to be turning at 33.4 radians per hour at that instant to be tracking it. Does that make sense to you? I mean, truly, math has always been motivated by our desire to kill each other, right? Humans, we're good at this, right? We're really good at this. Technology is pushed because we can't get along. All right, so what are we doing for homework? Let me look at this section. I'm going to start you out with the homework for this section. I'm just going to tell you out of the book what I would like for you to do. And just see how it goes, okay? Just see how it goes. We'll come back on Thursday and we'll do more of this. So for 2.7, let's try number 11. Number 13 is a plane, just like the one we just did. Number 15. Try number 27, that's going to be tough. Number 31. So look, of these problems, this one is basically the ladder problem. So it's giving you another opportunity to practice the ladder problem. Let me just look at it again. The top of a ladder slides down a wall at a certain rate. At the moment the bottom ladder is how? Oh, shit, no. Never mind. Don't do this one. That's a little harder than I wanted it to be. Hold on. Sorry about that. Do those problems, try those problems, and if you get through those problems, try number 12. Yes. Is it?
Yeah. Did you want us to turn this in and plug it down?
Just turn, yeah, look, at this point, I'm just wanting you to just try and keep up with this class, okay? I mean, it's these related rate problems, turn these in, you know, turn in what you can get through. I mean, I really just I want you to be learning. So really, I want you to understand this more than you worry about, oh, I better get every problem in, you know. But yeah, turn this in with it. Yeah. Yes?
The channels on it through to Thursday, so we would try Thursdays.
Say again, what?
This one, please.
Did I say Thursday?
Yes.
Oh, I'm sorry. You can take them back. Does anyone need them?
Hopefully there's
I forgot I said a week from, yeah, I did say a week, sorry. So if you need it back, does anyone need it back? You want it back? Yeah, it's due next class. It's a quiz grade for the chain rule. I apologize. I called for it in the beginning of class. All right. Good luck. Do this work. We're going to come back and do problems that are going to be